Okay, so good morning again. I will now present some experiments I've done on the direct component test, and more precisely on the estimation of bias and precision errors for this technique. So quickly, the principle of the direct component test is quite simple. It's the same than the fan pressurization test, in fact, except that we isolate the component of interest from the rest of the building. So here you have, here you have the pressure chamber that isolates the component from the rest of the building. I use a fan to pressurize or depressurize the box, and this pressurization increases the pressure difference between both sides of the component, and then the air flows out through the component, and we make the hypothesis under certain conditions that the airflow going in is the same as the airflow going out. The experimental setup in practice is more something like that. You have here, for this experiment, a plastic sheet that is isolating a window behind here from the rest of the building, and you have the other part, the duct that link the pressure chamber to the fan calibrated disc to determine airflow, manometer to measure the pressure difference and the airflow, and then a computer for data processing. And this equipment have a range of measurements that are here and there. Especially the interest part here is for the airflow measurement that is between 0.17 and 78.5 cubic meters per hour. I also use different design of pressure chamber. Here you have on the left side what I call the wood box system that is used to measure electrical outlets. And on the right hand side, you have the plastic sheet system with extensible proper bars that are used to divide the inflation of the plastic sheet in 3 parts in order to reduce the tense in the tapes, maintaining the plastic sheet in place. Before going to the experiment, a quick word about the data processing. So I used the Power law. I linearized the Power law. This is exactly the same as for the fan pressurization test. You have your measuring point here. Then you do a regression line. You have the airflow exponent that is given by the slope, the intercept, which is given by L and C, and you can deduce the leakage coefficient from this intercept reported at reference temperature. Then I have the air leakage rate at 50 Pascal given by this formula. And when I report the test, I report the air leakage rate at 50 Pascal in pressurization, depressurization, and average, and the airflow exponent in pressurization and depressurization. I did all the tests with the 2 regression techniques Vitor told about in his presentation, the ordinary least square, the weighted line of organic correlation, but in these results, it has no impact. So I will not go more in depth in those aspects of the presentation. I conducted 3 different types of studies. First, a validation study, then study to quantify one source of bias errors, and then different studies for precision errors. So the validation is quite simple. I tested 4 circular openings that are calibrated and that behaves using this equation. And I compared this to in-situ measurement, simple in-situ measurement of those calibrated openings. For the bias errors, I focused only on what I call the background leakage, which is in fact the airflow through the pressure chamber. And for the precision errors, I did repeatability tests, in fact 3 repeatability tests, one using the direct method with the plastic sheet system, using proper bars to improve it, one with the wood box system, and one with the wood box system, but I compared it with the indirect method, which is the same as the reductive sealing Vitor told us about, and that are the 2 main methods used in practice currently. So what is a repeatability test? A repeatability test is simply conducting multiple measurements on the same component using the same equipment and the test is conducted by the same operator. And under those conditions, the uncertainty of the method is assumed equal to the standard deviation of the test performed. This assumption, as any assumption, goes along with an uncertainty, and so error, and this error is given by this formula where n is the number of tests conducted. So if I increase my number of tests in my repeatability study, I will have a lower uncertainty in the assumption that the standard deviation can be taken as the uncertainty of the method. For the first experiment, you have here the result. On the left-hand side, in blue, you have the air leakage rate of 50 Pascal based on the calibration of the 4 openings tested. And on the right-hand side, you have the result of the measurements using the direct method. The highest difference in cubic meters per hour between calibration and testing was found for the 4th opening, and it's 4.28 cubic meters per hour. And if we are looking in percent, we have for the first opening, obviously, and it's 6% of the airflow measured. This difference can be due to 2 things. First, the measurement error that will provide random errors, and a background leakage that is a systematic bias. And when we are looking closer at the results, we see that the results from the direct component test are always higher than the calibration. And this really suggests that the background leakage has something to do with it. So to quantify the background leakage, I built a plastic sheet simply made of tapes, especially for airtightness application, and I taped my sheet on a wall, on a plastered wall, and then I tried to test this plastic sheet, assuming that its let's say airtightness performance it's much higher. So the air leakage rate of 50 Pascal would be much lower than my range of measurement, and then I can assume it equals to 0. And while testing it, I observed I still measured an air leakage rate of 4.17 cubic meters per hour at 50 Pascal, and this was the value I assumed for my background leakage. Then the repeatability test. The first study, I conducted 10 tests using the plastic sheet system, measuring a wood window and its interface with the wall. And my uncertainties were 10% for the air leakage rate at 50 Pascal in average, 4% and 10% for the airflow exponent in pressurization and depressurization respectively. For the wood box system, I did 20 tests using on an electrical outlet, and the uncertainty there were 5% in average, 3% and 2% for the airflow exponent in pressurization and depressurization. Then the third repeatability study that was used to compare direct and indirect methods. So I will not go deeply into the indirect method since Vitor told about us, but simply it's two fan pressurization tests and the sealing of the component between them. So we have Q51, Q52 for the 2 pressurization tests, and we have each of them with their uncertainty. And so you have the air leakage rate of 50 Pascal for the component that is given by the difference between both fan pressurization test, and the uncertainty of this air leakage rate is given by this formula that I will not give in more details. So I measured an electrical outlet in a laundry room. In fact, it was because of the COVID crisis, it was the laundry room of my apartment. I did 20 tests using the wood box system, and then in parallel, I also did 20 tests using the indirect method, but I limited the zone to the laundry room itself with an air leakage rate of 50 Pascal. That was around 80 cubic meters per hour. And that was the first result. I didn't know my laundry room was that leaky, but this is only of my own interest. Your interest is more in this graphic. So you have the black dots that are the mean of 20 tests on the right hand side for the indirect method and on the left hand side for the direct method. And we see that these are more or less around 3 cubic meters per hour for both methods. And in blue, you have the 95% interval that is calculated as twice the standard deviation. I should have stopped my blue intervals to 0 because there are negative leakage rates which have no many meaning. But the main difference here is really in the uncertainty of both methods. Here are the figures. So for the direct method, I have an uncertainty of 3%, and for the indirect method, an uncertainty of 60.5%. As a conclusion, I have the direct component test that measures in situ the airflow exponent and the air leakage coefficient values for building components with quite high reliability. I found in my repeatability test uncertainties are between 3% and 10%. That depends on the chamber design. However, the direct component test should not always be preferred over the reductive sealing, obviously, because it has a couple of disadvantages that the reductive sealing does not have, and so it should be really the tester should really select the appropriate test when needed. And among these disadvantages, we have that the direct component test must be replicated when measuring multiple components in multiple different components. It requires different pressure chambers depending on the component measured, and it uses another equipment than the fan pressurization test. In my opinion, the most promising application for the direct component test is for a worker, for example, to have a guarantee of good installation and of the quality of the work he did. Sorry. We have the possibility to conduct intermediate testing earlier in the construction process because it does not require the building envelope to be closed to do a direct component test. And it also provides methods to improve databases of building components with reliable in situ values that includes the airflow exponent, which is an interesting data when looking at when trying to understand airflow through building components. Obviously, the work is not over. There is a lot of further work that can be done. Here in my validation, I use large openings, so with an airflow exponent of 0.5, it could be very interesting to look at higher value of airflow exponents. There is a lot of work on the study of variables that influence the uncertainty of the method. And last important improvement, in my opinion, would be to increase the upper limit of range of measurements, because I'm currently at 78.5 cubic meters per hour, but we know that for leaky doors, for example, that are quite an important component in buildings, 78.5 cubic meters per hour may not be enough. So there is still work to do here. Thank you for your attention. I'm quite ready to have your questions.